Welcome to the Lake Lawrence Lake Management District Phosphorus Control Products Work Session. These are the virtual meeting rules that we'll be following for this presentation site. I'd like to introduce our next presenter on oxygen saturation systems. Paul Gantzer is owner of Clarity Resources Group. This is Paul's email. And Paul, with that, I'm going to stop sharing my screen to allow you to share yours.
Fantastic. So I will jump right into this. My background. I was a Navy nuke on board the USS Carl Vinson back in the late 80s. I'm a graduate from Virginia Tech in environmental engineering and water resource management focused. After I graduated from college with my Ph.D., I started Gantzer Water. And after we started developing OST and moved in more into this industry that we're in, we created Clarity Resources Group, where we specialize in oxygen and aeration. I've published over 20 peer-reviewed articles related to oxygen and aeration and water quality management, and we are patented in the United States, Canada, Australia, and New Zealand. So, really quick overview. My goal of this presentation is to be able to give you an overview or a quick summary of thermal stratification and anoxia, which you guys should be very familiar with already. Hypomagnetic oxygenation specifically. I want to explain to you what Oxygen Saturation Technology, or OST, is, how it works, and how it benefits oxygen management specifically related to iron, phosphorus, ammonia, and cyanobacteria. I'm going to cover some very quick basics of cyanobacteria, go over the kind of fundamentals of internal nutrient loading specifically related to phosphorus and the sediments. I'm going to go over what oxygenation would look like and how it would work for Lake Lawrence, and kind of do a quick efficacy of internal nutrient loading management. So with that, let's dive right into this. So why do we oxygenate? Well, the simple concept is thermal stratification. In the summer, the surface gets warm, the bottom stays cold. What ends up happening is this density gradient between the top and the bottom prevents the oxygen-rich surface waters from mixing with the bottom waters. And if you look at that as far as a dissolved oxygen profile, at this image to the left column is the depth and the bottom is time. The colors on the graph represent oxygen. White and red is low oxygen or no oxygen. Blue is high oxygen. So what typically happens throughout the summer, we have algae grow at the surface. This is why we have excess oxygen at the surface. We oftentimes have this detritus buildup, or this what's called a metalimnatic minimum, where that detritus dies and settles, and it creates this disproportionate oxygen demand in mid-water column. And likewise, we do have anoxia, or the lack of oxygen that builds up from the sediment up and pretty much dominates the lower waters. So, how do we get oxygen into water? Specifically, hypomagnetic oxygenation. Well, there's two ways. If we have a deep lake, we can directly inject oxygen by bubbling oxygen gas directly into the water column. We have enough hydrostatic pressure, the bubbles dissolve before they reach above the thermocline, and everything's fine and dandy. In shallow applications, we need to introduce some extra pressure to get that driving force. And oftentimes, you might have heard this called side stream saturation, or SSS. This is kind of the basis of how we came up with OST for Oxygen Saturation Technology. And that's predominantly for lakes that are less than 50 feet. So, what is OST? In a nutshell, it's an advanced aeration system. It's designed to overcome the challenges faced by traditional aeration methods for all forms of oxygen management related to any aquatic environment by blanketing the sediments with oxygen. It's a mouthful, but in a nutshell, it's a better way of getting oxygen in the water than regular diffused air. So, what are these components and how they work? Well, an OST system consists of 5 main components. We have our onshore oxygen supply. In this diagram, it's labeled as letter A. We have our umbilical, which is our oxygen supply, an engineered buoyancy line, and our power supply out to our pump. C is our oxygen contact chambers and our pump assembly. D is our automation, or an oxygen feedback loop, so we can monitor what's going on in the lake and turn the system on and off accordingly, just like a thermostat. And then the 5th portion are our suction and our discharge headers, which are engineered specifically to allow this movement of water at a very quiescent state so it doesn't stir up the sediments or induce any additional mixing in the water column. So, like I said, it is patented in the U.S., Australia, Canada, and New Zealand. And the key characteristics is we use pure oxygen, not compressed air. We have a buoyancy pipe that allows the entire system to be floated to the surface, to be serviced, and then sunk back to the bottom, so we do not need to have any divers to service our equipment. We promote this product with no bubbles and no induced mixing. This is why we can maintain thermal stratification, and we can actually just, quote, blanket the oxygen with sediments because we're very quiescently distributing that water along the bottom. It's designed to preserve thermal stratification, so if your lake is iced over, it won't destroy the ice. If it's stratified, it won't break stratification. It has this DO feedback loop, which provides us the ability to have automation to turn it on and off based on controls. And we can achieve 5 times higher oxygen than any other compressed air system on the market. And the last thing is, it's modular and it's scalable. So we can put multiple in one place, and we can increase the size of them for larger applications. So what do I mean when I say oxygen blanketing? Well, the concept is that the water is very, very cold at the very, very bottom. And if we can withdraw that water, get into the pump, and then redistribute that over time, that blanket of oxygen stays on the bottom. And the rest of the hypolynium gets oxygenated through dispersion. Some people have a hard time understanding this. So if we look at it graphically from actual data that's collected, and this is data that we collected in a lake in Cape Cod, we have 4 different DO probes positioned at 8 feet, about 8.5 feet deep, 13 feet, 15 feet, and 17 feet deep. And the 17-foot one is one that's inches above the sediment. And you can look at this data that's been collected over this summer of 2024, that the red probe, which is the one closest to the bottom, has oxygen significantly higher than the green probe or the yellow probe. Now, there is a blip in the middle, but that was a wind event. But as soon as the lake calmed back down, you can see higher oxygen at the bottom than there is in the bulk water. That is what blanketing the oxygen with sediment actually would look like. So let's look at some of the components. First one, our onshore oxygen generation system. This is simple. We need a compressed air supply that we feed compressed air to an oxygen generator. Or more specifically identified, it's a nitrogen stripper. That sieve allows us to retain the nitrogen and let the oxygen pass through, and then the oxygen receiver stores that oxygen to then distribute out to the lake. The umbilical, and we call it this because it kind of is the lifeline out to the system. It consists of 3 main components: the oxygen supply, the engineered buoyancy line, and our pump cable. And that pump cable is what's allowing to run our submersible pump out in the lake. The buoyancy line, like I said, it's an engineered structure like a gigantic ballast. When it's void of water, it floats. When it's filled with water, it sinks. So let's look at the chambers. The chambers you're going to see here are 3 different shapes. The middle one is where our pump is located. And water is drawn in at the bottom. It goes through the pump. And where it exits the pump, we inject oxygen that's coming from shore. That oxygen and water mixture then flows downward through that conical-shaped chamber. And the reason why we have that is as the water hits a larger diameter pipe, its downward velocity decreases to the point where it matches the rise velocity of a bubble. And it's that's the point where we get really good oxygen transfer. The water then continues down across the bottom into our secondary chamber. We call this our BCS, or our bubble capture chamber. And what happens here is any residual bubbles that are carried through coalesce at the top of this and have a chance to redissolve or get vented to the water column at a very controlled rate through an air relief valve, where the water then flows back down to this chamber and then back out to the bottom of the lake. So then the last component that's in the lake that works with the system are our engineered headers. And these are engineered to promote a very low velocity of water movement across the pipes. This is so we do not suspend any sediments and we do not entrain any aquatic creatures. The velocity gradient off our pipes goes to zero about 2 centimeters off the pipe. So it's a very, very calm, quiescent movement. We cover our pipes with copper mesh as a means for some additional anti-fouling to extend the duration that they can stay in the lake before they need to be cleaned. So the way this diagram shows you that we have our suction headers closest to the chambers, we have our discharge headers closest to us in the picture, and then we add feet to these so it allows them to set on top of the sediment, not sink into the sediment. And we can control the size of our feet and the size of the riser based on the type of sediments we're going to put the system on. The last thing, this is the nuts and bolts of the brains. This system has a DO probe that provides feedback to basically a small controller. That controller works just like the thermostat. We can program a set oxygen concentration at which the system would turn on and a set concentration at which it can turn off. And this is designed so we have true energy savings. When we need it, it turns on. When we don't need it, it turns off. Rather than throttle it, it is a strictly on-off application. So, and the last thing that we have with this is telemetry. So we have access to what is going on over the web. So, let's look at some strategies to control harmful algal blooms, or HABs. So first, what are we combating? Well, this is going to be a quick crash course in cyanobacteria. So, the main things I want you to take away from this slide, they're ubiquitous. Cyanobacteria and harmful algal blooms are not unique to Washington or New Jersey or Wisconsin. They're everywhere in the world. But the things that make them such tough buggers to deal with, these things called aconites. And I want you to remember that because we're going to come back to that again later. An aconite is like a seed. It can sit on the bottom and wait to the perfect carnode conditions to grow, and then it grows. And it can be there for a month. It can be there for years. And when I'm saying years, it can be there for hundreds of years until it waits for the perfect conditions. Cyanobacteria have gas vesicles, so they can move through the water column to get to where they need to, if they need sunlight, if they need nutrients. And worst of all, they can emit toxins to kill everything else off so only they can survive. So, yes, they can fix nitrogen and store phosphorus, but that's beyond the scope here. But the main things are gas vesicles, aconites, toxins. So, how do we control cyanobacteria? Well, there is a proactive way and a reactive way. Well, we're trying to get away from the reactive way. Well, first off, if I understand this correctly, Lake Lawrence is a very small watershed, and actually very small water flows into the lake, so your external controls would be very minimal for effects. But when it comes to reactive, we're trying to get away from dosing an algicide to fix it. So that leaves us with nutrients. Cyanobacteria's food. And the concept here is the phosphorus related to iron in the sediment. So, let's talk about nutrients. Phosphorus, or phosphate specifically. So this is going to be your one crash course in redox chemistry. So there's this concept called the electron tower. What that means is, simply put, in order to break down organic matter, to break down muck, muck needs to give up something. It wants to give up electrons. However, in order for that to work, something needs to accept the electron. The way that this tower works is that if something is present that's higher up, it gets preference. So as long as there's oxygen and it's oxic, oxygen will accept the electrons to break down organic matter. Once we lose oxygen and the lake becomes anoxic, well, in this case, the next viable source would be nitrate. However, there usually isn't very much of this. But as soon as nitrate's all burned out, the next thing available is iron. But for iron to do its job, it has to kick off its phosphorus, because that's what it's connected to accept its electron. So here's where loss of oxygen results in breaking that bond between iron and phosphorus, fueling your algal bloom. So, and it's this phosphorus, or this phosphate, that is this nutrient that we want to address. So, how does this impact internal loading, or this internal phosphorus in managing it? Well, we need to look at how phosphorus is bound to different compounds in the sediment. Remembering, this is all driven by the lack of oxygen or anoxic conditions. So, in your sediment samples, and I believe that I was provided with a breakdown of your sediment, I have two examples of what phosphorus speciation looks like. There are 5 types. Labile, which is readily available phosphorus to be consumed immediately. Nothing inhibits its uptake. Iron-bound, or FBP. That's how much phosphorus is bound to iron. Then there's aluminum-bound. That's the blue one, or ALP. Then there's organic-bound. That's the brown one, or that's called organic-bound phosphorus. And there's calcium. Calcium and aluminum are stable, especially in natural waters. However, under anoxic conditions, remember the electron tower? As we lose oxygen, iron is our source of phosphorus released to the water column. But the one thing we have to remember, or the one thing I want you to realize, is that when it comes to phosphorus speciation, it's the organic bound fraction that is the wild card. If you have a lot of organic bound phosphorus, that doesn't necessarily benefit a phosphorus management strategy, because phosphorus management is only related to the iron-bound fraction. And the graph at the bottom left shows what happens when you dose aluminum to the sediment. We don't get this surplus of aluminum-bound phosphorus from organic. It's an exchange. Aluminum takes the place of iron. So in situations where we have a lot of organic bound phosphorus, the aluminum taking up the iron doesn't necessarily solve our problem. And this is important going forward. So one more quick thing. This is going to be our quick introduction about the nitrogen cycle, or more specifically, what I like to believe is Oxygen Saturation Technology's silver bullet. Now, when algae or phytoplankton, which can be cyanobacteria or diatoms in green algae, for them to grow, they need nitrogen, an inorganic form of nitrogen to grow. So, on this nitrogen cycle, we are looking at where we are oxic and anoxic. So, when there's a lot of oxygen, that promotes what's called the conversion of ammonia to nitrate. Nitrate is the preferred form of nitrogen for diatoms in green algae. That's the good phytoplankton for the water column. Other organisms can eat that. That is a great source of food. If we lose oxygen and it becomes anoxic, well, remember the electron tower? What's the first thing that goes after we lose oxygen? Nitrate. So now we lose all of our nitrate in our anoxic process, and now we have a surplus of ammonia. Well, not only is ammonia bad, it's also the preferred inorganic nitrogen source that cyanobacteria need to grow. So now we have a surplus of ammonia favoring cyanobacteria, and we have a surplus of phosphorus feeding cyanobacteria. So this is where I like to introduce where oxygen management becomes a double-barrel shotgun. So research has shown that when it comes to oxygen management, specifically related to this ammonia nitrate situation, 10 milligrams per liter over the sediment. Some of you might think, 10 milligrams per liter, why on earth, how on earth would I get 10 milligrams per liter at the sediment-water interface? Well, remember that structure I showed you of DO and temperature? I want to focus in on the very, very bottom. And this is the predicted slope, the predicted rate at which oxygen depletes into the sediment. So I'm going to set that to the left. Studies have been shown that the higher we can get oxygen in the bulk water at the sediment-water interface, the deeper that oxygen will penetrate. So, some data collected back in 2024. We have good DO at the bottom on April 8th. I mean, it's positive, which is oftentimes plenty. But then when we boost the oxygen levels up even significantly higher, we project what that slope would be. We can see that low DO at the sediment-water interface goes to zero or crosses to zero fairly quickly or fairly shallow into the sediments. If we superimpose that same line to where we have higher oxygen in the bulk water at the sediment-water interface, we have to get deeper in the sediment to get to the anoxic boundary. So you want to say, why is this important? Remember that actinides I told you about? This is where it's a key player. Those actinides are known to sit on the sediment and wait for perfect conditions. So, if that actinide is sitting on the sediment where I have 1 or 2 milligrams per liter, but it's just barely touching that threshold, we have the ability for it to potentially be in contact with a phosphorus source, with an ammonia source. If we push our oxygen higher and that actinide sits on the sediment, it is so far out of range of that anoxic boundary, it can never get to its perfect conditions to grow. So, what would oxygenation look like for Lake Lawrence? So I'm going to show you the quick current design for Spanaway. And you can see Spanaway have a red rectangle up in the top right-hand corner of their topographical map showing the centralized location of 4 specific units, all being supplied oxygen from one central location. And the bigger screen in front of you kind of shows a close-up view how we have those positioned only in the deepest part of the lake. This is what we would propose for a system for Lake Lawrence. The same concept, focused on the deeper section. So, I didn't have a whole lot of information, so I bootlegged as much as I could off the internet. There's a Google map image on the right. There is a topo from, I think it's a fishing website on the left. And I made some assumptions if we were to put an oxygen supply at different locations. And that's what these 1250, 1300, 750 numbers represent. Because you have 2 basins, and they're separated by a shallow sill, they actually function like 2 separate independent hypolymnetic water bodies. In other words, the deep water of the main big basin has 0 impact on the deep water of the smaller, shallower western basin. In simple numbers, look that we would have 4 larger systems in the east basin and 2 smaller systems potentially positioned in the west basin. So what I've done is I've taken just a ballpark, what looks like a fairly unoccupied part of land, and did an estimate distance. Now, this is not set in stone. This is just a guess of where an approximate location would be. So you can see on the larger basin, I would have 4 units that are positioned right there off of that 750 line. Likewise, we could rotate those and move them off that 1,300-foot line. But either way, multiple systems in each basin to address the estimated oxygen demand of both of those basins that are on the top. So, you might ask, how on earth am I going to get oxygen added at the far north end of the lake down to the far south end of the lake when the lake is so big? Well, it's an excellent question, and I have great data to represent how this works. Back when I was at Virginia Tech, I did a lot of studying at the water supply reservoirs for the city of Roanoke. We had an oxygen system installed at the deepest part of the lake in front of the dam. And I was that kind of guy that loved data. So I would go out there and collect water column profiles all along the lake. And what we found is that we found oxygen dispersion over a mile upstream of our injection source. So if we can see oxygen levels in the 10 milligram per liter relative to our injection point at 13, we very easily could get distribution across Lake Lawrence that is 3/4 of that length. So, what would a building look like? Well, we would need 2 buildings. We would need an east footprint and a west footprint. And what I'm showing are estimated sizes for approximate oxygen generators that are proposed for the east side, which is a 10 horsepower compressor with what we call an ASE oxygen generator, that would fit in a 10 by 10 building. It would require 200 amp single phase power to run the compressor and run the pumps in the lake. The larger system would need approximate 12 by 16 building. For a 50 horsepower compressor, that would need 200 amp, but it would need 3-phase 460 to 480 volt service. 3-phase. Now, buildings can be any myriad of configurations. The top left shows a custom building that we had built for a project in Texas. The bottom left is a stock building that you can buy offline. The upper right-hand corner is a built-in-place block structure for the Capital Regional District up in Elk Lake, up in Victoria, BC, and that style was chosen because that matches every other building that the CRD has on property. And in the bottom right, that just shows a precast building, and they can come in any shape and size. So there's a myriad of different configurations that can be used for an actual building. And as far as security, none of these buildings have fences around them. They're not needed. They're just a locked structure. Actually, the one for the CRD, the built in place, that is literally 10 feet off of a running path around the lake. So there's been a big question. How do we secure our piping and our cables in the lake? Well, since everything is HDPE, and we shield our cables with HDPE, that piping is, in my personal opinion, relatively indestructible. Now, of course, you can destroy it by running it over with a Mack truck, but nobody's going to be driving a Mack truck on the bottom of the lake. We bundle all of our pipes with stainless steel hose clamps and then anchor them at set spacing with a concrete anchor. So not only is it all HDPE bundled, it has anchors every 15 feet. Each anchor weighs about 65 pounds. So if somebody were to put an anchor out in the water and inadvertently hook our umbilical, well, they just gave me their brand new anchor because they're not pulling it off the bottom. And oftentimes what we do for applications that are known to have fishermen in the shallows is we'll run a sleeve pipe, which makes it even harder to hook into any of the pipes. So the diagram on the right kind of shows a breakdown of some direct buried pipe underground, a sleeve pipe in the shallow part of the water, and then the pipes bundle themselves as they flow out each different respective unit. So what does day-to-day operation look like? Well, since we have it set in a thermostat, the automation takes care of itself. Now, there is mechanical equipment, and it's recommended to kind of stick some eyes on it once a day. However, for remote sites, and we have plenty of remote sites, we put their equipment on telemetry. So rather than have to somebody be there to babysit it, if a compressor loses power because of a power outage, somebody would get a text. If an oxygen generator turned off because a breaker tripped and we weren't getting oxygen in the lake, somebody could get a message that the oxygen levels aren't above the threshold that we would want. But there is this feedback that we can provide since there's already integrated telemetry into our systems. Maintenance. Now, what does the maintenance look like? Maintenance is divided into two sections. We have onshore-based maintenance, and that's just a regular preventative maintenance schedule for the compressor and the oxygen generator. It's typically biannually. Filters, changing the oil in the compressor. For the oxygen generator, we're going to service the canister filters. We'll service the solenoid valves every other year. But there's a regular scheduled maintenance schedule for that equipment. And it can either be performed by a Kaiser rep and or an AirSep rep, or if you have a maintenance guy that's, kind of got some smarts to them, this is not rocket science. It's relatively easy to manage this. The equipment in the lake is a different story. We've designed these to have copper mesh to minimize our biofouling, and we do that to extend the duration they can stay in the lake. Now, how often do they need to be cleaned? That is very, very dependent on your water quality. If you have a very eutrophic lake, a lake that's got a lot of algae growing and dying and settling, Yes, we want to raise this system. We want to inspect it. We want to clean it annually. If we have better water quality, and we've improved it, and there's not as much cyanos and not as much algae, well, we probably can get away with 2 or 3 years. We have had systems in place where they haven't been serviced at all, and we've had systems in place where they've had such hyper-eutrophic conditions that we're raising the system every 6 months because it's just getting caked so bad. And this typically can be performed by a lake management company. I know you talked to John or heard from John at Solitude. Now, John and his portion of Solitude wouldn't do it, but we do work with Solitude, and they would be a company. You're going to hear from Terry McNabb at Aquatechnics. We work with them. They would be a company that could do that. Or we could coordinate, and I could come out and do that as well. But again, there's a regular scheduled maintenance that would look like. So really quick, how do you recover these systems? Well, like I said, there's an engineered buoyancy line. We hook a compressor up on shore, and we push air into that buoyancy line, and the entire system floats on the surface. We go out there in a boat, we take a pressure washer or a trash pump, and we clean off our headers. Once we're all done, we pull it back into position, we connect a trash pump up to it, we pump water into that buoyancy line, and it sinks right back to the bottom, and we're ready to go. So, of course, you might say, this all sounds great in theory. However, will it work? So, I want to go over some results. So first off, the question, will it work? This is a copy of the phosphorus speciation data that I was provided on Lake Lawrence. There's 3 key things that I want to point out. Yes, we do have a fairly large iron-bound fraction. That's the boxes in red. Maybe not as much in the Big Basin E1, but Big Basin Deep, yes. However, you also have a very, very high organic bound fraction. It's kind of equal in the Deep Basin. However, Big Basin E1, you have a lot of organic bound fraction, phosphorus. And thirdly, is you have a very low iron to phosphorus ratio. So remember back at the slide I showed previously on the sediment speciation. Benefits work when we have a high iron fraction. When we have a high organic fraction, we start to work in this wild card efficacy. So what am I saying here? The point that we want to make, all phosphorus inactivation strategies only target the iron-bound fraction. Remember I showed you, as we add aluminum or any other phosphorus-binding agent, it actually trades the iron for aluminum, making iron available for something else. But when there's not a lot of iron, there's not a lot of else. Organic is the other else. So the bottom line is, more iron equals more iron-bound phosphorus. And the data on the right shows samples of data collected from several shallow lakes, showing the relationship of iron in the iron-bound fraction. If you don't have enough iron, you can add iron, and this helps make up for your organic bound fraction. So let's look at some results. Elk Lake is a direct oxygen injection system. It's up in Victoria, Canada. It's 608 acres, maximum depth of 58 feet. It was installed in 2023. In the focus of this project, it was kind of twofold. We were given a phosphorus budget, and we were given a caveat that we need to maintain trout. So we have to maintain cold water fish habitat. So the key things that we learned from that project, the first thing that we noticed is that ammonia, and remember ammonia is the organic nitrogen source preferential for cyanobacteria to grow. We had dramatic reduction in ammonia the first year that we operated the system compared to prior years. That's the data on the left. Phosphorus is a better story. Phosphorus, Elk Lake, like Lake Lawrence, has a high organic bound fraction. relative to their iron-bound fraction. They have a hypolymnetic phosphorus goal of 50 micrograms per liter. And the reason why they have that number, that matches their fall surface phosphorus levels. So when the lake flips, there wouldn't be a spike. We looked at their data and we did the math, and we estimated that oxygenation would only get them down to about 400 micrograms per liter. That's the green dotted line. The red circled dots are September data, and you can see that we had increasing phosphorus in the hypolymnium every single year leading up to oxygenation. After we installed it, we had an 85% reduction in internal phosphorus loading, and even though we budgeted that we would get to 400, the highest we saw was 290 micrograms per liter. So an 85% reduction with no other enhancement. They were jazzed. So another lake. Yes, I do understand it's very small, but when it comes to oxygenation and water quality response, it is equivalent. This work was performed and studied by Lake and Pond Solutions here in Wisconsin. And the bottom line is 86% reduction in total phosphorus in the bottom waters, a 67% reduction in ammonia. Remember we talked about ammonia is key for growing cyanos. Oxygen is key for getting rid of ammonia. So oxygenation targets both of those characteristics. And the last question people ask, okay, yeah, you knocked out ammonia. Yeah, you cut back phosphorus, but you still had some phosphorus. What did it do to HABs or cyanobacteria? This is where the Ceres Pond project, which is our first commercial installation, comes into play. We only added oxygen to this lake. And the reason why we only added oxygen, very, very high iron content in this lake. And you can see that the phytoplankton in this lake dramatically decreased over the last 4 years. I don't have current data, but this shows what the phytoplankton did since we started oxygenating the lake. So, yes, there you go. Proof in the pudding. We did reduce the cyanos from effectively managing oxygenation. So, Clarity's recommendation for Lake Lawrence, because I'm here more than just presenting OST as oxygen. Clarity provides a solution. So there's definitive evidence that iron and oxygen in shallow lakes can significantly reduce internal loading from the organic bound fraction. That's what Lake Lawrence has. It has a high organic bond fraction. So we as a company would recommend oxygen using OST plus an iron amendment. So really quick, before I get into the next slide, I'm hoping that you're able to take away so far the basics of thermal stratification and anoxia, how OST manages oxygen, a little bit better understanding of phosphorus inactivation and how it only applies to iron-bound phosphorus, the impacts of organic-bound phosphorus and how it's the wild card, and why a dual approach of oxygenation and iron amendment is recommended, specifically because Lake Lawrence has an iron deficiency and it has a high organic bound fraction. And lastly, understanding that Clarity's approach is focused on solving the problem, not just adding oxygen. So, what is it going to cost? So capital operational maintenance costs are listed. The ballpark high-level estimate for the OST system alone would be about $2 million. We don't know what a ZVI cost would be because we haven't studied that yet. And if I understand correctly, you're going to get a presentation from HEPPure soon. I think it's next week. We also work with HEPPure. We use their same ZVI for other applications. So I think they have a lot of good information to share. Operational cost. The slide I sent very earlier has a mistake in this chart. So this is the corrected one.
Got it.
And this is based on 6 months of operation at 3/4 of the time. For the 110 total horsepower in the west lobe, about $27,000 a year. In the east lobe, just under $5,000 for a rough total of about $32,000 in electrical cost alone. Now, that can go down over time, but for estimates out of the gate, that's what we would look at for the first year. Preventative maintenance, we're looking at about $7,000 of preventative maintenance annually. And the one thing I want to point out for the OST cost, because I don't have any information, and I don't think Herrera does, site work that would be required, a building, electrical, ventilation, permitting, taxes, so there's going to be some wiggle room there. So, how long will it last? If I'm spending $2 million, what am I going to get for my $2 million? So, from my perspective, are we talking about the equipment, or are we talking about the treatment? You know, oxygenation is not a service. You know, it's an actual, it's like thinking about a change in lifestyle. Application of oxygen is not a one and done. It's an ongoing strategy that's required for the life of the lake. So this question is being addressed from a mechanical lifespan, not a how long will a chemical dose last. So with that being said, the piping, it's written to last 50 years. The oxygen generator, to date, we know of no known failures so long as the preventative maintenance is adhered to. You provide clean, dry air to that sieve bed will last indefinitely. The compressors, it's mechanical equipment. You know, if you follow the PM schedule, you know, maybe a rough estimate that you replace the motor in 10 years or 20 years, but you don't have to replace the entire compressor, just components. And the only other mechanical equipment is the pump in the lake. And to date, I know of no known failures from the pumps that I've installed in 10 plus years of operation. However, I would budget for a pump once every 10 years as a kind of ballpark factor. So with that, how am I in time? I thank you.
Open it up for questions. Go ahead and raise your hand and I'll try to call on you. Frank, go ahead.
Yeah, just FYI, Pleasant Beach Drive has single-phase power only, the whole length. I don't know if Lindsay's three-phase is available or if there's like Lisa Lane area there. I assume that probably does have three-phase power because the Puget Sound Energy lines, you know, run up and down Lawrence Lake Road. They've got quite a few neighborhoods there, so likely they do have three-phase power there.
Okay.
So I don't know how you'd tie into anything on Pleasant Beach Drive.
Okay. Or probably Lake Point.
Yeah, likely that as well. Yep.
Okay. Any other questions, Frank?
No. That's just an FYI.
Thanks.
Cost FYI.
That's very, very helpful information. I mean, power is a huge factor when it comes to doing these systems. And the one thing that we do run into on occasion, we have power, it's a half mile away. So, I mean, we can run it, however, it just requires bigger cables. So the closer we can get our power to our shoreline, the smaller our cables are to run our system. So it's not impossible, it just becomes a hurdle.
Yeah. Janice?
Okay.
So you mentioned that with your system, we would want to add iron to our water. And so I'm wondering, is that more or less iron than, you know, the people will tell us to add if we did not have your system?
I don't know what HEPure is going to budget for the iron dosing. So oftentimes the literature says that your recommended iron to phosphorus ratio on a dry weight scale should be a minimum of 15:1. I prefer 25:1. If I can get 100:1, I'll go to 100. However, 100:1 might be kind of overkill. So the great thing about iron, we can mathematically look at how much you have and how much you're deficient to get to that minimum 15:1 threshold. There's your first dose. If you want a buffer to last a couple of years, 5, 10, let's look at what we need to do to get to 25 to 1. But it's a mathematical number that we can actually calculate because you actually have the data. So we would
in any case, in any case, you'll mathematically do the dosing. Would you need to continue to put iron in over time, or is your oxygen system preventing the need to continue to add iron over the years?
The hope would be, and we'd have to go and look at the way the budget would work. And when I'm saying budget, I'm not talking about a financial budget. I'm talking about the phosphorus budget.
Right.
We know how much phosphorus is bound up in organic matter. We know that organic matter is driven by algae that grows and dies each and every year. If we start to reduce each consecutive year's algal composition and subsequent deposition, we start to diminish that organic bound fraction. So it might be that we need 100 units in the first 5 years. By 5 years down the road, we need 10 more units. And then 5 more years after that, we need 2 more units or 1 more unit. We would have to look at how much are we getting phosphorus bound out of the organic fraction each year. And that we can do with a sediment sample. So you spend a few $100s to see how much progress we're making. That helps you do your budget. But I would hope that if we did like a 25 to 1 budget, that would give us a good 5, if not 10 years extension without anything else being added, just maintaining oxygen levels. Does it help? Does that answer your question?
Yeah, thank you very much.
I got a question for you, Paul. How tall is this unit that you put in the bottom of the lake?
That one is 12 feet tall.
Okay, so if we got a maximum depth of 20 foot in West Lake Lawrence, it's going to be only about 8 foot below the water.
So West Lake Lawrence is shorter. West Lake Lawrence is closer to 8 feet.
Yeah.
Because it's a smaller chamber.
In Lawrence, Kansas.
Okay.
So go ahead.
Well, I was just wondering what, the dimensions of the overall unit are. You said that they're 12 foot by, it looks like about 4 foot.
The ones in the deep basin are going to be an 8 foot square base, and they're about 12 feet tall.
Okay.
The one that would be going in the west basin, 4 foot base, and they're 8 feet tall.
Okay.
So the one thing I didn't talk about, and it's because it isn't really identified as a priority, muck and fish habitat.
Right.
Well, you get plenty of oxygen down there, you grow the right bugs, you're going to have muck reduction.
Right.
The Racine project that I showed you, they also did a sediment study. They saw a 8-inch reduction in soft sediments in the first year of operation with just adding oxygen. So there is natural reduction in sediments from getting oxygen down there. The other benefit, fish. We create a phenomenal fish habitat, especially cold water, because we keep the water cold, we don't warm it. Okay.
Okay, so who monitors the telemetry?
Whoever we want to.
Okay, so it's like an app on your phone?
Yes. Yes, that's currently what we're going to. We have a private system that we have installed in New Jersey, and it's run by a private organization. Mm-hmm. And it's an advocacy group very similar to yours. It's not as many, but that phone list is a page long. So when their compressor goes down because they have a phase out from dirty power coming from the New Jersey Power, 12 people get a text message. Hey, low pressure in the compressor building.
Okay.
And normally one person is close by. They can run over there and reset the compressor.
I was going to say, does that, it's got a switch inside that if you have an electrical outage or something like that, it's going to turn off. You got to go back and turn it on.
No,
Okay.
Before we did that system in Culver, the people that installed the Kaiser compressors forgot to set that programming. So the first year they're like, why do we have to keep going back and pressing start?
Okay.
Well, it turns out after you have to write the questions, we just changed the programming, auto restart. Then we have those systems set up so once the compressor's back on, oxygen generators detect high pressure, they can turn back on. We can start pushing gas back out to the lake.
Okay, what's the cost of the telemetry system?
It's included. Oh, so right now the annual or the monthly bill for that is about $25 a month.
Okay, so it's like through Verizon or TNT or whoever, or is it a different separate company?
We have Verizon modems, but we have private data plans.
Okay, and that's through you or somebody else?
We are working with another company, but we are looking at incorporating that into Clarity's footprint.
Okay. The other question is slide 26. It's Lake Lawrence. You got 6 systems. You got 4 large systems and 2 small systems. That's actually 1 generator system, but are those 4 of those 12-foot by 8-foot systems sitting out in the lake, or is it just the cables running to it?
Ask your question again.
Okay, so slide 26, you show 4 large systems in East Basin, 650 kilograms, and 2 small systems in West Basin.
Yep.
So are those the 12-foot by 8-foot and 4-foot by 8-foot, or?
Yes.
Okay.
Large systems are 8-foot base, 12 feet tall.
Right.
2 small systems are 4-foot base. Or no.
Okay.
Correct. 8-foot square, 12 feet tall, large. 4-foot square, 8 feet tall, small.
So
and I didn't include those in the presentation. I apologize.
That's okay, but my understanding is that those 4 systems are run off of 1 power station.
That's correct.
So what do those 4 large systems cost? Is it the $2 million approximately cost for all 6?
No, that $2 million is a complete total package for your oxygen supply, both oxygen supplies, all 6 systems, installation, telemetry, the entire package to get OST in your lake. Okay. It didn't include a building or your site work or electrical. I mean, we don't know what those are.
Okay. All right, so the $2 million is for all systems and installation, and except for the site work, building, electrical, ventilation, and permitting. Okay, Brian, go ahead.
Yeah, thank you. I didn't understand how you deal with the chemistry associated with the organic phosphorus. I mean, you talked about, I think you mentioned algae, but there's also a lot of other sources of organic phosphorus.
So, when it comes to the organic bound fraction that's measured in the sediment, I don't differentiate what it's connected to. That analysis that's provided is a macro observation that it's phosphorus bound to organic matter, not just algae.
Okay, so, but help me though with the chemistry of how your system converts the organic phosphorus into something inert.
It's not that it's converting the organic phosphorus to something that is inert. It's allowing that organic matter to be decomposed.
Yes.
And as that phosphorus is released from that decomposing organic matter, there's enough residual iron in the vicinity that it binds that phosphorus as it becomes available.
This is Paul's contact information, and if you have any additional questions that have not been answered yet, you can email me. Let me see. Here is our contact information at Lake Lawrence. If you liked this presentation, please give us a thumbs up. Here are a few other videos you might find educational and interesting. And hit the subscribe button in the lower right corner to get automatic notifications when the new videos are posted to this YouTube channel. Hope you all have a great day.